5, 4, day 1. Nice. Okay. What we're going to do today is find the mean and standard deviation of a sampling distribution. Okay. To find, it's kind of like a little theorem discovery here in this first example. You're going to find the relationship between a population mean and standard deviation and what we call a sampling distribution, the mean and standard deviation. There's a direct connection between the two. So I'm going to give you a very small population to work with. It's only going to have 4 members in it. 2, 4, 6, 8. So the first thing we want to know is what's the mean and what's the standard deviation of the population. Okay, the mean was easy enough, you could count it out 5. But the standard deviation, you're going to have to run your 1-bar stat. So if somebody will put 2, 4, 6, 8 in list 1 and run 1-bar stat. And we want the population standard deviation, that's the sigma one. Remember, your 1-bar stats gives you the mean and all kinds of information. We want the sigma off of that list. What'd you get, 1 point? No. Oh, I was going to say.
It would be like 3 points or 2 points.
Anybody? Somebody's got to do it. I'm not moving on until somebody does it.
2.23. I think it's about it.
2.24.
Yeah, 2.2.
2.24. Okay, now what we're going to do is make a sampling distribution choosing 2 numbers with replacement. And finding the mean of those 2 numbers. So we're going to be very organized with this. So we're going to make it's going to be a long table because we're going to take samples of size 2 from this population. So we're going to take 2 numbers out, find the average, write down the average. And we're going to do that till we've done all possible samples of 2 that we can take out of this. So it's going to be a big table. The sample, and then the mean. And I know it's going to take more than 1 column. Sample, and the mean, and maybe even 1 more. I don't know how big I'm going to write. So we're going to write down every single possible set of 2 numbers you can get by grabbing 2 numbers at a time with replacement. So let's grab a number, put it back, grab a second number, put it back. So let's be organized about it. Let's say I pick out the number 2 first. Pick out a 2, put it back in. What else can I get? A 2. What's the average of 2 and 2? 2. If I chose 2 first, what could be my second number? 4. What's the average of 2 and 4? 3. Now 2 and 6, the average is 4. 2 and 8, average is 5. Okay, that's it for picking a 2 first, correct? Now we'll go with the 4 first. 4 and 2, average is 3. 4 and 4. Average is 4.
What are the right two tables?
It's going to be, I'm going to run out of room. It's going to be all one big table. I just don't have enough vertical room to put all one big table here.
Good to know.
Huh?
Good to know. I have plenty of room.
Oh, not me. 4 and 6. Average 5. 4 and 8. Average 6. Okay. So I'm out of room, so I'm going to continue my table over here. Table continuation. Where am I at? 6 first with 2 gives an average of, how about 4? 6 with 4, average 5. 6 with 6, average 6. 6 with 8, average 7. And now my last set is 8, 2, average 5. 8, 4, average 6. 8, where am I at? 6, average 7, and 8, 8, average 8. Okay, so what I want you to do now is put all of the averages into list 1 and run 1 var stats to see what the average of the sample averages is and the standard deviation. So I didn't need my third table.
Five?
You got 5?
That's the average for all of them?
The average of the averages. So see how I've got population average because it's every single possible sample.
So, the X with the line.
Put all of the means in list 1,
Oh, just list one.
just list 1.
The X is equal to 5.
Okay, and then this is, it says the 5.
Okay.
And then what did you get for the standard deviation of the means?
1.5. Were you here for that? Again,
You are correct. Okay, so this is totally obnoxious to have to list all of these out. So we would like to have a nice connection between the mean of the population and the mean of the sampling distribution. Boy, tough connection there, isn't it? They're always going to come out the same. Now, the standard deviations obviously are different, and I could probably give you 5 years to see what the connection is. You probably wouldn't find it, so I'm going to tell you. So, let me write these, I think. So the mean, here's our 2 discoveries. First discovery, the mean of the population equals the mean of the sample means. Those are equal. The second property is that the mean of the population equals the standard deviation of the population. Actually, one more time. The standard deviation of the sample mean. To get this standard deviation, this one is equal to this one divided by the square root of your sample size. Let me write that better. The standard deviation of the sample means is the population standard deviation divided by the square root of the sample size. And I'm going to write those again on the next page. The problems that ask you to list these out again, do not do it. This is the only time I'm going to force you to write all of the listings out, so don't do it if they ask again in the homework. Got it? Okay. All I want you to be able to do is remember the 2 shortcut properties here. So let's make it nice and neat now, because I feel like I squeezed that in there. So the 2 properties of sampling distributions. of sample means. The mean of the sampling distribution is equal to the mean of the population. So the mean of the sample means equals the population mean. And the second property, the standard deviation of the sampling distribution equals the population standard deviation divided by the square root of the sample size. So, to distinguish between the two standard deviations, the population standard deviation is going to be referred to as the standard deviation. They refer to this one as the standard error. Standard error. Just to distinguish between the two. So now, can you apply these two properties to the next problem without having to make the big table? Let's find out. Everybody good?
Yeah.
Sam's good? All right. Find the mean and standard error of the sampling distribution if samples of size 5 are taken from this population. Zero through 9. Well, first of all, just think about taking sets of 5 from that with replacement. That would be 10 choices each time. 10 to the 5th power. That'd be a big table to try and make. So, in order for me to find the mean and standard deviation of the sampling distribution, so I'm looking for the mean of the sample means and the standard deviation of the sample means. That's my goal, get these two values. Well, I know there's a direct relationship between these two values and the population mean and standard deviation. So if you know the mean and standard deviation of this population, you can get these two values very easily. So the process here, enter these into list 1, run your 1-bar stats, find the mean and the standard deviation, but pick the right standard deviation, because remember there's 2 of them on your screen. So this is a 1-bar stat. We want the mean and the standard deviation here. He got a mean of 5. Did he pick the right standard deviation with the 2.58? I don't know. You want the population one, you want the sigma one. I have 2.87.
Yeah, I have 2.8.
Yeah, and I don't.
And then the mean is 4.8.
Do you have a 2.87 on your list anywhere?
No.
No. How'd you get the 5 right? Did you put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9?
Yeah, I have the mean of 4.5.
Yeah.
Oh.
Yeah, that's right.
You must have forgotten a number.
I forgot 0.
You forgot 0. 4.5 and 2.87?
Yeah.
Okay. So now what's the mean of the sampling distribution going to be if I take samples of size 5 from it?
She's recording now.
What's this going to be? 4.5. Means stay the same. How do I get this new standard deviation? It does change. It gets smaller.
2.87 by 9.
Divide 2.87 by the square root of sample size. I was taking samples of size 5. The standard deviation of the sampling distribution always shrinks, and it shrinks by dividing by the square root of the sample size, not the population size, the sample size. So what is the new standard deviation? There you go.
Wait. Oh, you're in error.
Okay. Good? Now we talk central limit theorem. Central limit theorem, which is the heart of statistics. That's not, I love statistics. This is the heart and soul of statistics right here. The central limit theorem describes the relationship between the sampling distribution and its population. So there's two parts to the central limit theorem. Say I've got a population of data and we make a frequency distribution for it, and say it's not nice and normal. We've been working with that normal curve. Say its distribution is just, I don't even know, not normal is my goal there.
Yeah, how does it go back in time?
Huh?
You gotta go in reverse.
I don't care. Well, so it's a little off. You'll survive it. My point here is that it's not normal. So make something that's not normal. Population, not normal. But, here, I'll fix it. You could still find the mean and the standard deviation. It doesn't have to be normal to find the mean and standard deviation. Any list of values has a mean and standard deviation. Now, if you take samples, something like it,
That's pretty good. Okay. I accidentally did normal distribution. I don't know how.
don't draw normal.
The one time I tried it not drawing.
Okay, if you take samples of at least 30 and make a sampling distribution, you know what magic happens? The sampling distribution turns out normal. 30 is a magic number instead. Who proved this stuff? I don't know. We just go with it.
It was actually statistics.
Okay. Now, the mean of this sampling distribution, just like we just learned, it equals the mean of the population. The standard deviation of this sampling distribution is going to be the population standard deviation divided by the square root of the sample size.
Get out of here.
Yeah, amazing. It's truly amazing. Okay? So it lets us do a lot of statistics for not knowing if the population's normal or not. You just gotta make sure you take 30 or more, and you can say a lot of stuff about that population, which you'll see. The second part, the second prong of the central limit theorem says, if your population is normal, we know that the population's normal.
I gotta flip the page.
Population's normal with a mean and a standard deviation. You can take samples of any size. So you don't have to hit that magic number of 30. You can take samples of 5 or 3 or 2 or 18. What's going to happen?
So it just has to be less than 30.
No, it can be more. You can still do more. It's still going to be, because if it's more than 30, it's automatically going to be normal.
Okay.
So you can take, but you can take any size smaller than 30, and you're still going to get a normal distribution. And the difference is, it's going to have the exact same mean, but that smaller standard deviation. So I'll just put it right inside of this one. Remember, smaller standard deviation is just going to make it narrower. So if you want to, if you've got the same color going on.
I do less now. Danny gives me.
So the mean of the sampling distribution equals the mean of the population. But the standard deviation for this blue graph is the population standard deviation divided by the square root of the sample size. Nope. I've got one last example. Short.
I have enough homework for nothing. I've been there.
Okay. Yeah, today's going to be a short day just because we got the quiz for half the people and all that good stuff. So example 3. Oh, was it 4? 4. The diameters of oak trees are normally distributed. With mean 3.5 feet and standard deviation 0.2 feet. I want you to sketch the population and sample distribution of size 16, finding the mean and standard error on the same graph. Oh, getting mean next door. Alright, so we'll start with the population. What do I know about the shape of the population? It's normal. What does a normal curve look like? That nice symmetrical bell curve. The mean of that distribution is 3.5. Standard deviation was given as 0.2. Now on that same graph, I want you to sketch the sampling distribution if I was to take samples of size 16 out of it. Well, it's under 30. Is it still going to be normal? Yes, because it's coming from a normal. And what's going to be the difference between the two normals? Just going to get narrower. That's the only difference. It's going to have that same mean, but it's going to be narrower. So there's the sketch of the graph. I asked you to list the new mean and the new standard deviation. Well, the new mean, how does it compare to the population? Exactly the same. How do I get the standard error? Take the 0.2, divide by the square root of the sample size. Sample size was 16, so 0.2 divided by 4,
0.05.
0.05. That's as much as I want you to do today. So it's two simple concepts. Very short assignment. Page 130, 1 through 4, 5 through 9, 11, and 12. Oh, 1 through 9, for gosh sakes. 1 through 9, 11, and 1 through 12, skip 10.
We just need to.
Okay.
And don't list the big tables out. Okay. Yes.